There is a window, narrow and precise, where the geometry of observation becomes hostile. When an object drifts too close to the sun, the instruments we trust, our wide-field surveys, our infrared telescopes, our carefully calibrated photometric arrays, begin to falter. Not because they fail, but because the sun itself floods the field. Scattered light dominates. Solar elongation collapses below safe operational limits. Background subtraction becomes an exercise in noise modeling rather than measurement. And in that window, when our traditional eyes go dim, something extraordinary happens. The object keeps moving. It keeps changing. It keeps interacting with the environment around it. An environment we can no longer observe through the lens of reflected light alone. 3 Atlas entered that window in the spring of 2025. A hyperbolic visitor, confirmed interstellar by the curvature of its trajectory and the velocity that no gravitational binding could explain. It was tracked, measured, and catalogued across months of inbound approach. Photometry refined, astrometry locked, spectroscopic attempts launched across wavelengths. But as it closed to within 0.3 astronomical units of the sun, the observational certainty began to erode. Not all at once. Gradually, like watching a signal fade beneath rising static. The paradox was immediate and unavoidable. The object was approaching the engine, the furnace of thermal forcing and plasma density that should make its behavior most legible. Yet from Earth, verification became harder with each passing day. Coma morphology became ambiguous. Tail orientation required model assumptions. Brightness evolution diverged between independent reductions. And into that ambiguity, a different kind of witness entered the same space. Parker's solar probe was never designed to watch distant comets. It carries no narrow-field optical camera, no spectrograph tuned for volatile emission lines. It is an in-situ platform, a sensor array built to measure the solar wind directly, to sample magnetic fields and plasma turbulence and energetic particles as they sweep outward from the corona. But in late April and early May of 2025, as 3An Atlas descended toward perihelion, Parker's solar probe was there. Not alongside the object, but within the same heliospheric neighborhood, carving its own elliptical path through the inner system. And that proximity raised a question that lingered like an unresolved chord. If the object was interacting with the solar wind in an unusual way, if it was driving plasma structures, accelerating ions, perturbing magnetic field lines, would we see it first in particles and fields, not in pictures? If you find yourself drawn to this unfolding mystery, subscribe for more Beyond the Solar Veil cosmic documentaries. The object was first detected on March 3, 2025, by the Atlas Survey System in Hawaii. A faint streak, moving against the stellar background at a rate that suggested something inbound and distant. Within 72 hours, follow-up astrometry from multiple stations confirmed the trajectory was not elliptical. The orbital elements resolved into a hyperbolic escape, eccentricity greater than 1, inbound asymptote tilted 12 degrees from the ecliptic, and a velocity at infinity of approximately 26 kilometers per second. Too fast to be bound. Too deliberate in its path to be a recent ejection. The catalog entry was issued, 3A Atlas. The third confirmed interstellar object. Distance context became the clock against which all subsequent observations were measured. At 3 astronomical units, roughly 450 million kilometers, the object was faint, showing minimal activity. At 2.0, subtle coma development began to appear in long-exposure imaging. By 1.0, gas production models suggested water sublimation should be accelerating, dust rains lifting from the nucleus, tails forming under radiation pressure, and ion pickup. But as the distance continued to collapse, from 0.80 to 0.5, then 0.4, the geometry turned hostile. Solar elongation, the angular separation between the object and the sun as seen from Earth, dropped below 30 degrees. Observing windows shrank to narrow twilight slots. Ground-based telescopes faced sky glow and atmospheric extinction. Space-based assets entered safety protocols. Hubble's fine guidance sensors cannot operate near the sun without risk of scattered light damage. GEBDUSD voids the inner zone entirely to protect its thermal equilibrium. SOHO's coronagraphs, designed for solar monitoring, lack the resolution and calibration to track faint cometary features reliably. The object was not invisible. It was simply difficult. Measurements became noisier. Calibration harder. Background models more uncertain. And yet, in that same period, Parker's solar probe swung through its 23rd perihelion pass, reaching within 6 million kilometers of the Sun's surface. Its instruments, plasma analyzers, magnetometers, particle detectors, wide-field heliospheric imagers, were fully operational, sampling the environment every fraction of a second. The probe was not watching 3 Atlas, but it was inhabiting the same heliospheric volume, moving through the same solar wind structures, the same magnetic sectors, the same turbulence cascades. If the object was leaving a signature in the medium itself, a wake, a perturbation, an anomaly in the local plasma, Parker's solar probe would have been in position to measure it. The months leading up to the blackout window were rich with data. Pan-STARRS and Atlas provided nightly cadence photometry, tracking brightness variations with 0.05 magnitude precision. Gaia contributed astrometric positions accurate to milliarc seconds, refining the orbit and constraining the object's rotation state through positional wobbles. Hubble captured high-resolution imaging in ultraviolet and visible bands, resolving coma structure down to 100 kilometers per pixel at closest approach. JWST attempted mid-infrared spectroscopy, searching for thermal emission and silicate features, though the signal remained at the limit of detection. Subaru deployed adaptive optics and narrow-band filters, isolating CN and C2 emission lines to estimate gas production rates. ALMA scanned for millimeter continuum, probing dust grain size distribution and mass. TESS, repurposed during a sector crossing, provided high-cadence photometry at 2-minute intervals, searching for outbursts or periodic modulation. Each platform measured something real, but what they measured did not always agree. Surface brightness profiles showed central condensation consistent with a point, source, or unresolved nucleus, but the slope of the outer coma varied depending on aperture size. Color indices ranged from neutral to slightly red, depending on whether the photometry was extracted from the inner coma or the diffuse tail. Spectroscopy found weak CN emission, but the column density implied a lower gas production rate than photometric models predicted based on heliocentric distance scaling. ALMA detected thermal continuum, but the inferred dust mass was lower than expected for the observed optical brightness, unless the grains were unusually small or the albedo was higher than typical comet material. Amateur observers, using 8-inch and 12-inch Schmidt-Cassegrain telescopes with cooled CCD cameras, stacked hundreds of 60-second exposures and reported extended tail structures that professional reductions flagged as potential background contamination. The disagreements were not contradictions of bad data. They were the natural product of measurement at the limit, where every choice in reduction pipeline introduced subtle bias. But as the blackout began, something changed. The data stream did not simply go quiet. It became contradictory in ways that resisted reconciliation. Near the Sun, the physics should be clear. A comet, or any volatile-rich body, responds to increasing solar flux with predictable mechanisms. Ice sublimates from the surface, driven by absorbed radiation and thermal conduction into the interior. Water, carbon monoxide, carbon dioxide, and methane follow distinct temperature thresholds, each volatile activating as the Sun's energy reaches deeper. The escaping gas drags dust grains with it, lifting particles from micrometers to millimeters in size, entraining them in the outflow at velocities of a few hundred meters per second to over a kilometer per second. Radiation pressure from sunlight pushes the dust grains outward, segregating them by size and creating the characteristic dust tail. Meanwhile, ultraviolet light ionizes the gas, and the solar wind's magnetic field sweeps the ions into a separate ion tail, stretched along the local magnetic sector. The coma itself is a collision-dominated region where gas molecules expand, cool, and dissociate under solar photons. Spectroscopy can identify parent molecules near the nucleus and daughter radicals farther out. Dust optical depth determines how much light scatters back to the observer, and the phase angle, the Sun object Earth geometry, dictates the brightness through forward versus backscattering efficiency. As heliocentric distance decreases, production rates should rise steeply, often scaling as r to the -2 or -2 or -3 power, depending on the volatile's activation energy and the nucleus's thermal inertia. At 0.30, roughly 45 million kilometers from the Sun, the flux is 10 times stronger than at 1 STI. Surface temperatures on a low albedo nucleus can reach 400 Kelvin. Supervolatiles like carbon monoxide, with sublimation temperatures near 25 Kelvin, would have been active since the outer solar system. Water, dominating near 1 should now be boiling off at kilogram per second rates for even a modest nucleus. Dust grains, accelerated by radiation pressure, should form a broad fan, with synchrones marking the time of release and syndines tracing the force balance between gravity and radiation. But 3I Atlas did not follow the script precisely. The solar wind adds another layer. A comet is not an inert target. It is a source of mass loading. Nitro gas escaping from the nucleus moves outward, unaffected by electromagnetic forces, until it ionizes. Once ionized, the particles are picked up by the magnetic field embedded in the solar wind, creating a local perturbation. The solar wind slows, deflects, sometimes drapes around the obstacle. In extreme cases like Halley's Comet, a bow shock forms tens of thousands of kilometers upstream. Even a weakly active body can leave a detectable wake, pick up ions, wave turbulence, magnetic discontinuities. These signatures are not visible through a telescope. They are written into the plasma itself. So the expectation was straightforward. As 3I Atlas descended, it should become brighter, more active, more gas-rich, and more dynamically coupled to the solar wind. Near the Sun, physics should become more legible. The measurements should converge. The models should tighten. Instead, the opposite happened. Astrometric residuals, differences between observed positions and the gravitationally predicted trajectory, grew systematically. Non-gravitational acceleration, a standard feature of active comets, was detected, but the magnitude did not match the outgassing models derived from spectroscopy. The acceleration vector was offset from the expected radial direction, suggesting either a strong rotational torque or an asymmetric outgassing pattern that persisted despite changing illumination geometry. When teams corrected for the acceleration and refit the orbit, the residuals shrank but did not vanish. A low-amplitude, quasi-periodic pattern remained, too subtle to be definitive, but too persistent to ignore. Photometry became unstable. Between 0.5 and 0.30, the object brightened, then dimmed, then brightened again, all within a span of 12 days. The variations did not match the smooth R-squared illumination curve. Outburst models could explain a single brightening event, but the dimming phase implied either a sudden drop in dust production or a change in scattering geometry. Phase angle corrections were applied. The dimming remained. Rotational modulation was considered, but the timescale was too long for typical comet nuclei unless the object was unusually large or elongated. Fragmentation was proposed, but no secondary components were resolved in high-resolution imaging. Tail morphology presented its own puzzle. The dust tail, when visible, was oriented roughly anti-solar as expected, but the inner coma showed subtle asymmetries, brightness enhancements that rotated over several days, suggesting localized jets. The jets did not align cleanly with the Sun's direction, implying the nucleus was not a simple sphere uniformly heated. Fine diegetic. Many comets showed jets, but when the photometric models tried to account for the jets, the predicted light curve did not match the observed one. The timing was off. The brightness peaks lagged the thermal forcing by hours to days, longer than standard thermal models allowed, unless the surface was insulated by a thick dust mantle. Yet spectroscopy showed gas production, which requires exposed ice. Different teams, using different pipelines, reached different conclusions. One group measured a steady dust-to-gas ratio of 2. Another found it variable, ranging from 0.5 to 5 over 2 weeks. A third saw no clear correlation between CN column density and continuum brightness. All three groups used reputable methods. None made obvious errors. The object was simply operating near the edge of what could be cleanly separated from noise and systematics. And then the blackout began. Solar elongation dropped below 20 degrees. Observing windows closed. The object crossed into the zone where only Stereo A and Parker's Whisper instrument could image it. And those were designed for large-scale heliospheric structure, not precise photometry of small bodies. The last reliable ground-based measurements came on May 2nd. After that, the object was effectively invisible to the world's telescopes. But it was still there. Still moving. Still interacting. Explanations formed a spectrum. On the conservative end, asymmetric outgassing from a rapidly rotating nucleus, where the jets turned on and off as active patches faced toward and away from the sun. Reasonable. Testable. Could explain non-gravitational acceleration and brightness variations if the rotation axis was tilted. Could explain tail asymmetries if the jets were clustered on one hemisphere. But it struggled to explain the timing lags and the photometric residuals that persisted after correcting for rotation. A step further, fragmentation into a weakly bound cluster, multiple components orbiting each other at velocities of meters per second, too close to resolve individually but dynamically distinct. Fragmentation would increase effective surface area, boost gas production, and create complex light curves as components occulted and scattered light differently. But fragmentation events are usually abrupt, triggered by tidal stress or spin-up, and no outburst coincided cleanly with the onset of anomalies. Another possibility, a dust-rich gas-poor regime where most of the mass loss is solid grains, rather than volatile vapor. Radiation pressure on dust can mimic rocket forces, creating non-gravitational acceleration without detectable gas emission. The dust could be fractal aggregates, low-density, high cross-section particles that absorb and scatter light efficiently but carry little momentum. This would explain why thermal continuum was faint despite optical brightness, and why spectroscopy found weak gas lines. But it required the object to be compositionally unusual, more like an asteroid shedding debris than a typical comet. Further still, supervolatiles trapped in the interior, sealed beneath a refractory crust, suddenly venting when thermal waves reached critical pressure thresholds. Carbon monoxide or methane pockets could store energy and release it episodically, driving jets without steady sublimation. This would explain delayed responses and timing lags. But it predicted spectroscopic signatures, CO or CH4 lines, that were not clearly detected. And at the edge, swarm-like behavior, a hypothesis defined not by mechanism but by observational pattern. If the object were not a monolithic nucleus, but a distributed system, many smaller components, loosely coordinated, it could exhibit collective dynamics that mimicked propulsion. Acceleration without single-point thrust. Brightness variations from geometric reconfiguration. Spectroscopy diluted across many sources. It was not a claim of artificiality. It was a mathematical model space. What would the data look like if this were true? And if true, what would Parker's solar probe detect? Parker measured plasma. It measured magnetic fields. It measured energetic particles and solar wind speed and density fluctuations. In late April, as 3I Atlas crossed into the inner heliosphere, Parker's instruments recorded the environment at 6-minute cadence. Proton density, electron temperature, magnetic field magnitude and direction, wave power spectra. Ion composition ratios. All of it telemetered, archived, available for post-processing. The challenge was separating signal from background. The sun is not quiet. Coronal mass ejections erupt every few days. Extreme interaction regions collide where fast wind overtakes slow wind. Magnetic switchbacks, sharp reversals in field direction, occur hundreds of times per orbit. Every one of these creates signatures in the data. A transient increase in density could be a solar event or a pickup ion cloud from the object. A magnetic deflection could be a sector boundary or a localized draping structure. Timing mattered. Geometry mattered. Repeatability mattered. And so the question became, in those weeks when telescopes went blind, did Parker see anything unusual? Did the plasma data show a perturbation that tracked with the object's predicted ephemeris? Did the magnetic field record a deflection consistent with mass loading? Did energetic particle fluxes spike in a way that correlated with the object's trajectory through local solar wind sectors? The data exists. The analysis is underway. Peer review has not concluded. But preliminary whispers, informal, unconfirmed, suggest anomalies. A localized density enhancement that appeared within Parker's field of view during a close approach window. A magnetic field rotation that did not match the expected interplanetary sector structure. A brief elevation in pickup ion counts. Composition uncertain, timing ambiguous. None of it definitive. All of it intriguing. The kind of signal that demands more work, more cross-checks, more campaigns. Because the object is not finished. Perihelion occurred on May 9th, the closest approach to the Sun, where thermal forcing peaked. Post-perihelion, the object began its outbound journey, solar elongation increasing, observing geometry improve. By late May, ground-based telescopes could target it again in darker skies. Photometry resumed. Spectroscopy restarted. The light curve could be compared to pre-blackout data, testing whether the object's behavior had fundamentally changed during the hidden window. Predictions now become tests. If the object was driven by standard sublimation, the post-perihelion brightness should decay smoothly, tracking the inverse square of heliocentric distance. If it fragmented, secondary components might now be resolvable. If supervolatiles vented, spectroscopy should show different molecular ratios. If it was compositionally strange, the dust-to-gas ratio should remain anomalous. Multi-longitude campaigns are being organized. Observers in Australia, Chile, South Africa, and Hawaii will coordinate to provide continuous coverage, eliminating gaps where transient features might hide. Photometry will use standardized apertures and background models. Spectroscopy will target multiple species, CNN, C2, C3, NH2, H2O+, to map production rates and validate gas-dust coupling. ALMA will observe again, searching for thermal evolution and grain properties. Dynamically, the object will remain interesting for years. Its trajectory carries it past Jupiter's orbit in 2027, where planetary perturbations could shift the outbound asymptote by a few kilometers per second. If non-gravitational forces continue, the orbital elements will drift further, complicating long-term tracking. Eventually, 3E Atlas will exit the solar system entirely, becoming another data point in the growing catalog of interstellar visitors, each one unique, each one challenging assumptions. Science does not demand certainty to be meaningful. It demands honest measurements, careful models, and the patience to let nature answer in its own cadence. The blackout was not a failure of observation. It was a reminder that some questions cannot be answered with light alone. That particles and fields carry information too. That the environment itself can be a witness when traditional telescopes go silent. 3 Atlas came from somewhere beyond the sun's influence, traveled through the coldest reaches of interstellar space, and then plunged into the furnace. For a brief window, it moved through a region where we could not see it clearly, but where the physics was loudest. What Parker's solar probe recorded in that window may yet rewrite what we think we know, not about alien visitors, but about how matter behaves when caught between starlight and solar wind, between gravity and radiation, between the certainty of prediction and the humility of measurement. And if the data confirms something unusual, something that resists the easy explanations, then the question is not whether we believe it, but whether we are ready to build the instruments and the campaigns and the theoretical frameworks to measure it properly. Because the universe does not owe us clarity. It only offers the chance to look more carefully, to ask better questions, and to recognize that mystery is not the absence of knowledge. It is the presence of something waiting to be understood.